In an earlier lesson about surge protection methods, the point was made that air valves are devices typically used to treat the symptom of negative head in a system. The trap for engineers analysing transients in such a system is to focus only on head performance, the symptoms of surge, rather than fluid velocity changes. Ignoring pipe velocity performance in these cases can be a significant omission. It has the potential to lead to unexpected outcomes that are not easily explained by simply looking at head performance. This lesson explores the subject that air valve sizing can be critical and how air valve size can influence pipe velocities. Air valves are frequently used with the design objective of limiting minimum head, for example, after a pump has stopped. It is helpful for engineers to understand two things about air valves. The design objective is usually satisfied when the air valve first opens, and two, subsequent opening and closing of air valves, if they are oversized, can cause large, localized surge events of their own, often leading to lower minimum heads and higher maximum heads. Let me lead you into this subject with a story. The story involves 4 players. Introducing the first player, the pipe. It is a 450mm polyethylene sewer pressure main, slightly more than 5 kilometers long. It is PN 12.5. That pressure rating means that it will easily cope with the maximum surge heads. Introducing the second player, its air valves. We come back to them later. For now, meet the pipe's owner and the rule book. The owner and the rule book make the design objectives quite clear. Heads as low as vapor head will not be tolerated. The owner prefers to avoid adding surge protection measures other than air valves on sewer pressure mains. The owner even specifies the preferred type of air valve based on minimizing air valve maintenance. The rule book even suggests the size of air valves that the owner is familiar with and comfortable installing on sewer pressure mains. This all pleases the fourth player, the consultant engineer. The owner's rule book makes the consultant's design task easier. It helps shape the surge protection solution. Just install air valves along the pipe route and make them the owner's preferred size and type. So continues the story. The pipe's biggest problem is low heads, created each time the pump stops under automatic control. The downsurge will cause the wastewater to vaporize in the downstream half of the pressure main. Maximum surge heads are not a problem, falling well within the pipe's pressure class. Consequently, the consultant engineer develops a solution, implementing the idea to install air valves along the pipe route of the owner's preferred size and air valve type. The minimum surge envelope is expected to fall not much below the pipe obvert level, as seen in this anticipated profile. Turning the next page of this story, we find a sad disappointment. Minimum heads drop quite low in between most of the air valves. The owner's rule book will not be satisfied by the idea because the wastewater will vaporize at isolated locations between air valves. Is the consultant's idea of air valves along the pressure main wrong? No, the consultant's idea is an inherently correct concept. The use of air valves at the chosen locations is fine. The low head problem is being generated by the wrong size of air valves. The air valves are too big. Let me pause the story at that point. It is a very common story, repeated often for many utilities on many projects. Let me explain a better approach to the analysis of air valves on pumping mains. We will keep the design objective of controlling minimum head. After all, it is a valid goal stated in the owner's rulebook. However, we should consider the steps in the design process to be 1. Do a series of transient analyses with different size air valves to understand the velocity outcomes in the pipeline. Then select the air valve diameter that effectively limits velocity changes in the pipeline. Finally, select the velocity change scenario by virtue of air valve size that results in minimum heads that satisfy the owner's rulebook. How does air valve size impact compressive wave behavior and pipeline velocity in between air valves? To answer that question, we are going to look at the behavior of the compressive waves for three alternative designs. 1. The pipeline in our story without any air valves. 2. The pipeline with 100mm Ventamat air valves along the route. And 3. The pipeline with 25mm Ventamat air valves along the route. Plus, we will look at the behavior of pipeline velocity at the midpoints between the air valves. Looking at these velocities will help us see what is driving the surge amplitudes experienced in the pipeline. Starting with case number 1, no air valves. Let's look at the compressive wave and the pipeline velocity changes as a pipeline long section. I'm going to step out of view to let you see the whole screen. The pump turns off. We see a strong downsurge in pressure travel up the pipe, large enough to create negative heads in the pipeline. Note the top velocity graph. Note that after the pressure wave has passed a point in the pipeline, the fluid velocity is dropping to 0. And this pattern continues until almost 12 seconds have elapsed in the simulation. Vapor head level is reached because pipeline elevation has increased. Fluid vaporizes at some locations, and wave reflection returns some locations to the fluid phase. Vaporization and fluid column separation allow parts of the pipeline to stabilize to different velocities. The downstream fluid column is only slowing to about 0.3 meters per second. This pattern continues until 20 seconds into the simulation when the pressure wave reaches and reflects off the discharge manhole at the end of the pipeline. Pump stop has vaporized a large downstream portion of the pipeline, making this an unacceptable design option. We engineers have lost control of the fluid. Okay, we saw how pump stop affected head and velocity as a pipeline long section. And in the interest of time, that presentation ended at about 28 seconds into the simulation. Beyond that time, the reflecting wave progressively increases head and returns various portions of the pipeline into the fluid phase. In time, the whole content of the pipeline will come to rest, yet not under our control. Now let's take a look at the system's behavior in terms of the rate of change of velocity at the pipe midpoints. That is halfway between the sites where air valves will be installed in the other design options. Noting, of course, that acceleration is the rate of change of velocity. This graph of midpoint accelerations shows that a lot happens after the 28-second point in the simulation, driven by vaporization and recombination of the fluid column, leading to large fluid accelerations and decelerations, and eventually the system coming to rest. Zooming in to look at the acceleration patterns in the first 30 seconds, the graph looks like this, with the large positive and negative acceleration values occurring after the initial pressure downsurge reflects off the discharge manhole at the 20 seconds mark. So let me zoom in once more to look just at the first 20 seconds. What we observe from this graph is, as the initial pressure wave arrives at successive midpoints, here, here, and here, for example, there is a sharp deceleration of the fluid in the order of 1.6 to 1.3 meters per second squared. After 12 seconds, vaporization and fluid column recombination allow a whole sequence of more rapid and less controlled fluid accelerations. We engineers lost control at the 12-second mark. Let's move on to case 2, 100mm Ventamat air valves. Again, we start by looking at the compressive wave and the pipeline velocity changes as a pipeline long section. The pump turns off. We see a strong downsurge in pressure travel up the pipe. Watch the top velocity graph. Note that the fluid velocity is not dropping to zero everywhere, like we saw in the previous case. As the wave passes each air valve, the fluid continues flowing downstream at a fixed rate, while the fluid upstream of the valve decelerates further. It is this velocity behaviour that prevents head in the pipeline falling not much lower than the pipe obvert, well, at least during the early stages of the transient event. This pattern continues until 20 seconds into the simulation, when the pressure wave reaches and reflects off the discharge manhole at the end of the pipeline. So far, so good. The current hydraulic grade line resulting from the first transit of the pressure wave is quite acceptable. Yet looking at the minimum and maximum surge envelope lines, we engineers must lose control of the fluid during later stages of this transient event. Back to looking at the system's behaviour in terms of the rate of change of velocity at the pipe midpoints, halfway between air valves. This graph of midpoint accelerations shows that after the 20-second point in the simulation, there are two distinct later stages. The first up to about 90 seconds, due to air valve and fluid responses without any vapour pockets forming, and the second after 90 seconds when vaporization and recombination of the fluid column increases the fluid accelerations and decelerations. Zooming in to look at the acceleration patterns in the first 30 seconds, the graph looks like this. Again, large positive and negative acceleration values occur after the initial pressure wave reflects off the discharge manhole at the 20 seconds mark. And zooming in to look just at the first 20 seconds. Note from this graph, the initial pressure wave arriving at successive midpoints, here, and here for example, shows the same sharp deceleration of the fluid in the order of 1.6 to 1.3 meters per second squared, as the case without any air valves. After 16 seconds, the interaction between the fluid and air valve operation introduces fluid accelerations that are much larger than generated by pump stoppage. We engineers appear to have lost control after the 16 seconds mark. So what does case 3 with 25mm Ventomat air valves look like? The pump turns off. We see a strong downsurge in pressure travel up the pipe. As we saw previously in the top velocity graph, as the pressure wave passes each air valve, the fluid continues flowing downstream at a fixed rate, while the fluid upstream of the valve decelerates further. Head in the pipeline is not falling much below pipe obvert during the early stages of the transient event. The pattern continues until the pressure wave reaches and reflects off the discharge manhole at the end of the pipeline. The current hydraulic grade line resulting from the first transit of the pressure wave is quite acceptable. Looking at the minimum and maximum surge envelope lines, we engineers must have maintained control of the fluid during later stages of this transient event. The maximum surge envelope is only slightly above the initial hydraulic grade line, and the minimum surge envelope is what we're trying to achieve. Looking at the system's behaviour in terms of the rate of change of velocity at the points halfway between air valves, there is a dramatic difference compared to the previous two cases. They both resulted in larger accelerations after the first transit of the pressure wave, that is, after 20 seconds. With smaller 25mm air valves, we are now seeing the largest accelerations happening during the first 20 seconds. Here are the acceleration patterns in the first 30 seconds and in the first 20 seconds. Note from this graph The initial pressure wave arriving at successive midpoints has the same sharp deceleration of the fluid in the order of 1.6 to 1.3 meters per second squared as the previous two cases. Later interactions between the fluid and air valve operation show much smaller accelerations. We engineers appear to have control of this design. To understand why this is happening, let's look at a direct comparison of the 25mm and 100mm Ventamat valves at a single point along the pipeline. We will look at a typical location, being sector 7, which is here. To start, consider the different responses to the initial downsurge from the pump stop. Up to the time of arrival of the initial pressure downsurge, all three cases behave the same. There is the same rapid deceleration of the fluid. Without any air valves, the fluid continues to decelerate, but at a reducing rate. As we saw in the earlier long sections, the velocity continues to drop towards zero. In both of the Ventamat valve cases, they behave similarly after the initial sharp deceleration. They admit air into the pipeline, allowing the fluid to continue at a velocity of just over 0.6 meters per second. In other words, admitting air stops the deceleration of the fluid. This is what allows the head to be kept just below pipe obvert level. This all looks like what we engineers needed to see happen to meet the design objective of sustaining the minimum head at an acceptable level. So what is going on during the later stages of the surge event? We can ignore the light grey velocity graph and acceleration graph of the no air valves case. Here and here we see instances of the 100mm Ventamat valves at each end of pipe sector 7, allowing fluid accelerations of the same magnitude as the original sharp drop caused by the pump stopping. Yet when these accelerations occur, the hydraulic grade line is not well above the ground profile, it is down near the pipe obvert. End result, negative minimum heads, and at times low enough to reach vapor head. Yet if all that changes is the size of the air valves, in this example changing to 25mm Ventamats, their orifices sufficiently constrain inflow-outflow to reduce these fluid accelerations to about 1/3 of those generated with 100mm valves. Air valve size is critical. Air valve orifice size determines the degree to which your design can control fluid velocity changes. To reinforce this same point, look at the difference in velocity envelopes and head envelopes between the 25mm and 100mm Ventamat valve cases, toggling between the 25mm case, 100mm case, back to the 25mm case, and back to the 100mm case. Can I rest my case? Air valve sizing is critical on many projects, particularly long pipelines using multiple air valves for surge protection. Initial opening of the air valves is what typically meets the design objective, but subsequent opening and closing of the air valves will cause local surge events. The head amplitudes caused by these local events will have an average level close to ground level. The larger the air valves are, the larger these head amplitudes will be. My case for successful design of surge protection using air valves is this. Analyze the velocity and head outcomes generated by a range of air valve sizes. Select an air valve size for your design recommendation that constrains fluid velocity sufficiently to deliver the head control that the pipeline owner requires.